So last time we left off, we were talking about electron configuration, and we talked about how we designate the different energy sublevels with that, and we use different notation. So for carbon, for example, it's 1s2, 2s2, 2p2. So that indicates that we've gone through this first 1s level. So we've got 2 electrons there that took us through helium. We've gone through the second 2s level, which has taken us through beryllium, and we're going over to the 2p level to finish out, and that's going to be 2p1, 2p2. So that's the notation, the electron configuration for carbon. And we went through and we discussed sodium and iron, bromine, and barium as well. And I left off on seaborgium. Seaborgium is going to be a longer one because we have to go down to the F level for that one. So we're going to do 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then remember we have to go down that -1 for the D level. So this is going to be 3D10. Then we go through 4p6, go down here, 5s2, 4d10, 5p6, 6s2. And this is where we have to go down here then. So this is period -2, which is 4. So this is going to be 4f14. Then we go back up here, which would be 5d10, 6p6, and then we go down here, 7s2. Down here, period -2 again, so that's going to be 5f14. Then we go back up here, 6d1, 2, 3, 4. So 6d4. And that's how we end up with the electron configuration that we have written up here. All right, so how do we make that simpler? Well, for that last one that we looked at, we could use actually what's called noble gas notation, which takes it down, and you have to go back to your previous noble gas. So for seaborgium, that would be Rn here. And for seaborgium, the way we would write that would be, and we would put the Rn here because that's our last noble gas. And then we go through and we write everything that would be past that. So we would just rewrite all of this stuff right here. So that ended up being 7s2, 5f14, 6d4. And that's how we would do the scientific, kind of the truncated or the shortcut method using the noble gas for the electron configuration for seaborgium. So you can see the one here for sodium would be Ne because that's its previous noble gas, 3s1. So let's try that with cobalt here. For cobalt, cobalt is right here on our table. So we would end up going back to the previous noble gas, which would happen to be argon. So we would go Ar. And then we finish out here. That would be 4s2. And then this is 3D. And we have to count over 1, 2, 3, 4, 5, 6, 7. So 3D7. So that takes care of cobalt. All right. So let's look at silver. Silver then is right here on our periodic table. So its previous noble gas is going to be krypton. So we're going to do krypton here. Kr. And then we go back to over here where that would have ended. So that is 5s2, and 4D, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that is silver. All right, tellurium then is found right here. So for that one, the previous noble gas again is krypton. So we go over. This is going to be 5s2. Four D10 and 5P4. So that is tellurium. Radium is a pretty easy one because it is right here. So we're not going to have to write a whole lot for that one. So for radium, I'm just going to write it down here because I ran out of room and I didn't erase. So radium is going to be, go back to the previous gas, which is radon. So Rn, and then it's going to be 7s2. And that's it. That's all you have to do for that one. That one's pretty easy. So then the next one that we're going to do is polonium. And polonium is found right here. So for polonium, we are going to go back to the previous noble gas, which is xenon. And we go back over here, which would be 6s2. Then we have to go down here, which is 4f14. Back up here, which is 5D10. And then finally 6P4. And that would be how we would write polonium. So that just gives you kind of a shortcut method so you don't have to go through all that extensive stuff. And here's a couple other examples of shortcut methods. Now, the last thing that we need to talk about is valence electrons. And with valence electrons, they're the electrons in the outermost orbitals. That's always going to be your s and your p orbital after you've written it in this kind of shorthand method. So for here, you would add the s's and the p's together. So 2 plus 4 is 6. That would be how many sulfur has. For cesium, it's always going to be 1, and francium, it's always going to be 1. So that's pretty easy. The electron dot structures then are going to be important when we get into bonding in chapters 8 and 9, and it just makes it easier to visualize. So you need to know how to do electron dot structures, and we just simply write those or represent those valence electrons with dots. So the dots are going to be placed one at a time around the 4 opposing symbols. So for example, if we had chlorine. Okay, chlorine has its truncated method here for chlorine would be neon, Ne, and it's going to be 3s2, 3p5. So that means if we add 2 and 5 together, it's going to be 7 electrons. So we're going to start off, and we do them one at a time around. So there's 1, 2, 3, 4, and then we double up, 5, 6, 7. So that's how we end up doing electron dot structures. And you can see here that we have other examples of electron configurations. So here, lithium its outer electron configuration would simply be this 2s, so it has one electron. Here we have 2 electrons. Down here we would have 4 electrons, and notice that they don't double up until we get more than 4. So that's how we end up writing electron dot structures, and you'll have to do those as well for this chapter. So I hope that helped you with truncated or shorthand method for writing electron configuration, and also how to write electron dot structures.